Hey everyone, how are we doing? It is office hours today on the 27th. What problems are we working on? Who's got a homework problem or a quiz problem or questions about the test? Let me know if you're in the chat right now who has a problem. Let's take a look at it. See, you have a question on Discord. Da-da. No worries right there. No worries. There we go. Head back over to here. What questions are there? Let's see what questions people have. Hey, Layla, good to see you here. Canvas content number 10. Can we do a certain story? Yep, we did one of those today, and we'll do the second one. Simran says Canvas content. Which one? We see 2 votes for Layla's question. Let's do Layla's question here to start. Then we'll hop over to Canvas content. Let's do this. And thank you, everyone, so much for being here. Let's do this. Let's do the... We did one of the 2 war stories today. So let's go get the other war story right here. Did I seriously just click on it right away? I think I did. Yeah, I think I did. I think I actually just went to it. Wow. Wow. Let's do this. Let's hop over here. Hey, Cad, good to see you here. Let's hop over to the main screen. Let's do this. William's going to be mad. I went and got more straws and put them in my coffee. Oh, no. That's why I spilled my coffee, and William says, see, I told you. Okay, so we need help right here. Oh, Mewbot should be awake, right? Is Mewbot awake? Mewbot's awake. Good job, Mewbot. So with this right here, Mewbot's always here. Oh my God, it's evil Mewbot. So with this right here, what is the null hypothesis going to be? What trick do we use when we get to this right here to do the null hypothesis? Is it A, B, C, or D? Which of these will be the null hypothesis? A, B, C, or D? Which of these is going to be the null hypothesis? A, B, C, or D? Now, there should be a clear way of knowing it because we're doing the chi-squared test of independence. So since we're doing the chi-squared test of independence, one of these is going to jump out instantaneously and be like, yep. And I think you're right, Cad. Yep. It's going to be B because we say that the 2 are independent of each other. And then there's a lot of ways of saying like they're not independent, like they are associated or things like that. So make sure to mention that the 2 values are independent of each other as I try to rip cords out of my computer. Don't do that. So now we get down here to the expected values. This is where it can take a while. To get the expected values, it's row total times column total over grand total. Let's just find one of these by hand to make sure we can solve it. Remember the formula is row total, like right here, 12, times column total over grand total. So the row total is 12 times 64 and divided by 141. And that is the expected cell count for arrow body right here. So we have one of these just so we can check it. But now we're going to find all of them pretty quickly using jump. Go here to the table and go to copy to clipboard. With the table copied to clipboard, we're just going to hit Control or Command C. So copy the data table to the clipboard. Click right here, copy to clipboard, Control or Command C. With Control or Command C clicked, we're now going to go over to jump and go to a new data table, File, New Data Table. With File, New Data Table clicked, we're going to go inside of the new data table and go to Edit, Paste with Column Names. And I'll pause right here. So just open up a new data table, make sure you have it copied, make sure to paste with column names. That's huge right here. So we copied the data table. Now we're going to paste with column names. And let's go ahead and paste with column names. You've gone through... CAD, that's what I like to see right there. Yep, that's great, right? That's what I want to see. And hopefully I'm doing it slowly now so people can be like, okay, we're just going to paste it. What are we going to do next, CAD? You probably know. Now that we have this pasted in here right here, we're going to go here to tables and we're going to go to stack. We're going to go to tables and we're going to go to stack. I've had instructors ask me, hey, Brian, can you walk me through these steps again? Because I solve all these problems here. And sometimes you just forget how to solve one, but you know, this is just how to do it right here. We can do it by hand, but you know, we got that one practice that we solved one by hand. Let's just do this right here. When you stack them, you're going to click the blue ones. It's going to stack the quantitative columns. I'll pause right here for a second so you can see what's going on. And then we're going to click OK. This will create the data table for us that we can use to do the analysis. Now that we have the data table created right here, we'll go to Analyze and then Fit Y by X. Make sure you have the data table with 2 categorical variables, one quantitative. You can relabel column 1 to, you know, weapon or something like that. But yeah, And I think that should be weapon. Does the weapon explain the site of injury? Now, here's the key mistake people make. One of the mistakes people make is that they do not put the data right here. Make sure you put the data right there. So make sure where data is at, you have that right there. If you don't put data right here, you're going to have a bad time. It's not going to work out. So make sure to put data right here, and that's what we should have. So let's make sure we have that. Click OK. And now we have the answers. There's all the answers. Let's go ahead and find the expecteds. I'm just going to remove everything I don't want to see. Frankly, all I want to see is the expecteds. I'll show you what that looks like here in half a second. I just brought back the column totals, the column percentages. And now let's go here and just put the expected values. So now that we have just the expected values, I'm going to take a screenshot of it to bring it over here. And let's take just a screenshot of this. These are only the expected values so that we can focus just in on these and make sure they go in the right spots. No, it'll still do the analysis the same way. You just have to make sure. I might have flipped mine. Oh, I didn't flip mine. Okay, good. If you flip them, you just have to make sure they go in the right spots. If you notice, we did calculate this first one right here by hand just to make sure we could solve it. We could have probably done this just as fast by doing it by hand. Got to be careful with your numbers. But calculate one of these just to make sure you can solve it by hand. You know, row total times column total over grand total is the expected cell count. So if you can solve one of them by hand, you can get the rest of them in the jump table, and you can understand that it's showing right now only the expecteds. So following these steps right here and doing a little bit of practice is a big help. Make sure they line up like body, body, head, neck, limb, limb, arrow, arrow, ground, rock, sword. If you flip them, you can reflip them. A quick way to redo it, let's say you flipped it, CAD. If you flipped them, you can go in here to jump and go to the top and go to redo, relaunch. That is redo, relaunch. And if you go to relaunch, you can go back up here and switch these two around. So if you did switch them and you want to switch them now, and it'll still give you the same numbers. It'll be, can we do the Age of Football? Yeah, we're going to do some Canvas content, and then we can do that one next. You got it, Haley. Great question. And thank you, everyone, so much for... people use these office hours a lot. A lot of people have told me office hours are a huge help, and it's thanks to the people here asking the questions. And thank you to the people who watch it, too. But it's always hard for me when if I have to do the questions on my own. Then I'm like, no, I don't have anyone here to talk to. No one's here to keep me company while we solve the problems, and it's no fun. Only one decimal place... it should be right, Layla. Tell me if it gives you a wrong answer. Tell me, I'm fine with decimal place. If for some reason it's like it counts off because of a decimal, just tell me. I'll probably get one wrong because of a decimal. I'll probably type one of these decimals in incorrectly, the wrong way. And if that happens, just tell me, be like, hey, Brian, I was entering the numbers and I forgot a decimal, or I rounded up or I rounded down. I'll be like, whatever, you understand the work. We're not here to teach how to round. We're here to solve statistics and understand what the chi-squared test statistic is. The chi-squared test statistic for this problem is the sum of all the cell chi-squareds. That's something we should understand theoretically right here, that if we were to look at just these cell chi-squareds right here, and we were to add them all up, now they're pretty tiny. Yeah, they're pretty tiny right here. So that means we see right here 2.571 is the sum of all these values. These are all the cell chi-squareds. So 2.571, so 2.57. Since the chi-squared is pretty small, the p-value is going to be pretty big. A pretty big p-value is one that's closer to 1. And the p-value down here is the Pearson, or the Pearson has your chi-squared. So the p-value is 0.632. Type the whole number. Wait, how many degrees of freedom? 4 degrees of freedom because it's a 3 by 3. 3 by 3, subtract 1 on each, 2 times 2. And then we should have the p-value. So 4 degrees of freedom. 3 decimals. I think it was this. And we definitely do not reject the null. We do not conclude that they are independent. We fail to reject the null hypothesis at the 0.05 level of alpha and do not conclude that site... my gosh, that would get me right there. We do not conclude the alternative. We continue to believe the null hypothesis, but we do not conclude the alternative. That almost got me. It's saying we do not conclude the alternative. And just checking my p-value right here, make sure I have the right p-value. Degrees of freedom are 4, because 3 by 3, 2 times 2. And that should do it. Hopefully I typed in all those correctly. Whoo, got a little bit scared there. Always got to hold your breath. Sometimes it'll be a decimal that will just get you. Or that one almost caught me right there because we failed to reject the null hypothesis. We do not have evidence for the alternative. That's all this is saying. Like this whole everything over here is just saying we do not have evidence for the alternative. So we do not conclude that they are not independent of each other. It's saying you do not have evidence for this. And you know, so we've seen that before where it says like we do not have evidence for the alternative hypothesis. This final statement right here is I do not have evidence for my alternative hypothesis that they are not independent of each other. They like to switch up the wording to make sure you know what's going on, and they'll try to catch you off guard on that. I would say I continue to believe at this point that they are independent, or, you know, like that's my current belief because I started with that and I ended with that. I think it was Canvas content next, the final Canvas content. Let's do this. Let's listen to some more 80s music. Here we go. Some chill 80s music right here. Some like vaporwave 80s music. We've got the sports teams. Was it football? Where is it? I saw it. Where'd it go? There we go. Haley said, oh no, we're going to do Canvas content first. We're going to do Canvas content. Coffee woke me up there. Okay, let's do Canvas content. And with Canvas content, oh my gosh, look at this. We're so close to done. Canvas content. We'll do 2 versions of the Canvas content. Here comes version 1 of Canvas content. Here we go. The expected cell count frequency is based on the researcher's opinion. Help me out here, everybody. If I remember correctly from today, we have a certain formula for the expected cell count. It goes something like row total times column total over grand total. Is it based on someone's opinion, the expected cell count is this formula we were covering today, row total times column total over grand total? Is that based on my opinion? Yep, we did that. Yep, Layla. And we can do that later if you want. We did both of them. The end of lecture today had the final one. I think Haley asked it at the very end of lecture. So if you go to the very end of lecture, and then we did the homework at the start of when we started doing it. I'll put the timestamps in a little bit later. That's 100% false. Row total times column total over grand total. If you're looking for the more complicated one, it's the very last bit of lecture. The overall chi-squared test statistic is found by doing what to all the cell chi-squared values? So what do we do to all the cell chi-squared values? What do we do to all the cell chi-square values to get the to get the Pearson? And we've talked about this a lot right here. I'm going to put on just the fun music today. What do we do to all of them? We add them up. Exactly. We're going to adding them up. We're going to be adding them up. Sorry there. The Pearson chi-squared test statistic is the sum of all the cell chi-squareds. Chi-squared tests are used for testing hypothesis association between 2 categoricals. What is the condition related to 2 categorical variables? Which kind of tells you about this. What condition do we have which states that we need 2 categorical variables? Or like the condition is met by being 2 categorical variables. What condition do we have? I'll show it here once someone says it. What is the condition related to 2 categorical variables, which kind of tells you the answer to this question. What is the condition? And this is a good way to review, because then you don't just want to guess. You don't want to be like, I think that's right, maybe. Count data, exactly, Cat, right there. Remember that regression is 2 quantitative variables. So the condition of count data, which you see right here, is that there's 2 categorical variables. And that means we're doing the chi-squared test of independence. So 2 categorical variables is being used right there. Which of the following is not a requirement for a 2-sample t-test? You better bet random is. What also is always required? Which of these 2, like random / what? Like, you're always gonna, we're down to 2 now. We're only, if you know the next, like you always do random, you always do 10%, and then we pause. And then you'd have to say, well, wait a minute, what am I dealing with? Which I have to go grab that picture again. So we pause. We should know this picture I'm going to show here in a second. There's the picture. So the conditions that we always have are random, 10%, success failure, and CAD knows the answer right there. It's going to be independent means. You see the color coding right here. Blue is for quantitative. So if you have two quantitative variables, you go down here. This is just my color coding way of remembering what we do. You always do randomly selected data. You always do less than 10% of the population. Those are the first two conditions always. Success failure is for categorical data. This one's for quantitative. That one's sampling distributions. Nearly normal is what we usually do. This one's only for sampling distributions where we do large enough n. Expected cell count and count data are what we did today for the chi-squared. There are no orders to these. To me, it just makes sense to put them in some sort of way that we can help memorize them. And this right here hopefully helps. I hope this has helped somebody memorize them. So independent means is the one we do, which is not a requirement. Ooh, wait. It says which is not a requirement. I almost did which one is. The success failure is the only one that is not a requirement because the success failure is for categorical data. I almost got caught off guard right there. So the success failure is the only one that is not a requirement because independent means we need when we have two independent means. Yes. You know what I might do? I might fix my camera in a moment. The sample size of each group must be the same for the two sample t-test. I think I still have the applet maybe up. I don't. Yeah, we can do another version of this. We'll do one more version after this. I'm gonna try to fix my camera between this. I'm gonna fix the so as everyone see right here, is this true or false? What do you think for this last one? The sample size for each group must be the same. And you can see we were doing some work earlier. And here we go with one of the problems we just did for, where did it go? I just saw it. Here we go. Here's a problem we did, and the answer is up here. The sample size must be the same for the two groups. So the answer to the question, because we did this test, is right here. That is 100% false. You can have different size groups for each one. So you can see in this question, we have a different size group. So the answer is definitely false. We'll do another version here. So we should have 100. My head's going to just explode. I'm just going to be like, we don't get that 100. We'll do another version right here. But I'm going to try to fix my camera really quickly because my chair and my mic are all sparkly. So let's, I'm going to try to fix my camera, which to fix my camera, good, it's this one. I need to fix. It's all sparkly. It's actually better, and I think I fixed Tiny Brian also. Tiny Brian, you doing better, man? Doing better?
I'm way better. Whoa, you fixed my camera. Okay, wait, 2 seconds. Gotta fix Tiny Brian. Where's he at? You bet we can do that here. Yeah. Okay, there we go. Okay, got it all fixed.
There we go. Okay, that's, wow. The things I break, not meaning to. Okay, so let's do the second version right here. We'll hop to space so I can put a cut in the video so everyone doesn't have to see all the camera fixing. Yeah, it was this weekend when I guess when we did the haircut stuff, I changed a setting. Man, I'm using 2 filters, and who'd have thought it actually works? Let's do one more version of the Canvas content. Let's do it here. Here we go. Camera's looking better. That's what we like to see. Okay, second version of the Canvas content. Let's preview it. Here we go. Okay, question number 1. A contingency table is a key component in understanding the chi-squared test of independence. What do you think? True or false? A contingency table is a key component. The answer is on the screen right now. Is a contingency table, make this smaller so we can see it all. Is the contingency table a key component, true or false? What would you say to this? Is the contingency table a key component in understanding the chi-squared test of independence? What would you say to that? Someone says, do you know, hey, the contingency table is a key component in understanding the chi-squared test of independence. What would you say? I would say most definitely what? Because here's the analysis of it. The mosaic plot and the contingency table are shown. Most definitely what for this? Most definitely true. Yeah, definitely. Contingency table is a huge key component of it. The chi-squared tests are often used to hypothesize of the association between two categorical variables. I think we just did this one. That's the condition right there of count data. We just did that one. The degrees of freedom for the chi-squared test of independence are 5. Oh, I hate that way the photography looks. What are the degrees of freedom for this test? Are they 5? What are the degrees of freedom for this? Go ahead and put the degrees of freedom for this in the chat. I'll give you a hint. Here's the hint. Unless I'm miscounting. That's not the answer. So what is the answer to this? What are the degrees of freedom? You say, Brian, this is a what by what? The formula is this. So we practice a lot. They're 4. So this is false right here because this is a 2 by 5 or 5 by 2, whichever we want to do it. And then we just drop down by 1 and we get 4 times 1. So we're just saying there's 5 columns here, 1, 2, 3, 4, 5. Do not use the totals. That's a very common error. There's just 5 groups right here. And then there's 2 groups right here. You just look at the categories, like the outcomes have 2 outcomes. The main category has 5 categories, 2 by 5, 2 by 5, reduced by 1, 1 times 4. This is false. There are 4 degrees of freedom. The sample size for each group must be the same. We were seeing this earlier. No, no, no. If you look at many of the problems we do right here, we can find another one, a different one we did. Surely we have another one. Nope, that's P times Q. We should see another 2 sample t-test. There's the courtroom from yesterday. Here we go. Here's a 2 sample t-test. Oh, the sample sizes are the same. Well, that's a bummer. It's the bike problem right there, and it has the same sample sizes, but this one does not have the same sample sizes. You'll see a lot of questions. Can you do the one, was the p-value for on the Canvas quiz? Yeah, let's try to find that one. Here, we'll do that one next, Layla. You got it. A poll classified response by gender. Yep, you got it. We'll do all those, definitely. And this is definitely false right here. Let's try to find that Canvas content, then we'll hop over to doing more Pearson. You got it. That's false. And below is this the one you were talking about? I don't think this is the one. Below is jump output of the difference between 2 means. So we have right here, calculate the test statistic. Ooh, someone calculate this for me. We were doing this a lot yesterday. And I'm going to show some output. I think I actually just found some. Okay, here's output. Who can calculate the test statistic here in this output? Who can go to this output and calculate the test statistic? This one you can see the answer on. So take a moment, and this will help, and find the test statistic in this output. You can see the answer. So take a moment. You bet, Simran, Lift, definitely. We've got some great questions lined up. You have the same question as Layla. How about we do that one next here? We'll do Layla's. Is that a Canvas content or I think that's a Pearson, right? And then, so how would I get this test statistic right here? How is this value being obtained from this output? How is that value being obtained from that output? How is that value being obtained? It's Canvas content? Good, we'll find that one. Definitely. How is that value being obtained from that output? How are we getting that 16.51966? how can that, it's going to be the test statistic, which is just the difference divided by the standard error. So how would we get that right here? How are we mathematically finding that? What is the mathematics I could do right now to find that, which will help us solve this one? Because we're missing this portion of the output right here. What can we do to just solve and get the t ratio, which is just the difference standardized? So basically write the equation in the chat right now for how we would get this number. So we just need to take the difference and standardize it. So what mathematically are we going to do? We're going to divide those two numbers. So if you divide those two numbers, you can get the answer, which is what we're doing over here on the Canvas content on this question right here. We're just going to take the difference, which is not a way to check the nearly normal condition. Which of those sounds like not a way, CAD? Good question, CAD. Which of those sounds like not a way? Let's take the difference and standardize it. So which of those sounds like not a way, CAD? I want you to tell me which one you think sounds like not a way. Round to 2 decimals. There's the answer right there. Oh, you can't see it. Which of those sounds like not a way? You know what? I think we should have that this is a plus or minus. Which of those sounds like not a way to check the nearly normal? And then why? Yeah, that's what I'd like to see. Which of those sounds like not a way to check the nearly normal and why? Let me see if I can find... Okay, one sec. Good job. You got it, CAD. You got it. Think about what kind of data they work with. Think about what kind of data they work with. Like when you look at the things we would use, be like, oh, well, this uses a this uses a this uses a this. So I don't know if we would do that. Think about what kind of data they work with. So Simran is saying it is fall. Is it a poll? So you're saying there's a question, like I'm going to have to look through the questions. I'm not seeing it. Should eventually get it. Can you put the start of the question again? Why? Everyone has the question. I don't. Wait. Oh, you're wondering about this one right here. Which one, CAD, the degrees of freedom? Well, that sounds, unless the question is different than what I thought it is. Can you put the full question you're asking, CAD? Oh, and then we have right here. Oh, we got this one. You ready? So this one's a little tricky. Let's take the values right here, and I need help with this. Let's take the output. This is a great question. And let's bring it over here to a worksheet. And so when we have this is the right one? Awesome. So this might be a little confusing. And then I think there's another one that Simran wanted that maybe Layla was asking about too. Brian is shading in the what p-value right now. Just put a symbol in the chat. Brian is shading in a what p-value right now. I'm shading in the what p-value. Like just put one symbol in the chat. I'm just shading in the this p-value. So I've just shaded in the this p-value because here is my... Hey, what's up, Charlie? So good to see you. Thanks for swinging by. Are you taking 320 this summer, is it? Or am I just like going crazy? There's our t ratio right here, which is this value. The other one I was asking about is on Chapter 19 quiz. Yes, awesome. That might be the one Simran was asking about too. I think so. And so I'm shading in the which p-value here. What p-value have I shaded in? Like which direction of a test? Which direction of a test? No, next semester. Awesome. I'll be seeing you in class. Or I'll be seeing you in office hours. Which p-value have I shaded in right here? The what tailed test. Think about the yellow shading. Which p-value is that? It's the less than, exactly. So this is the less than test right here. And how about that p-value? Can you tell me what this p-value is right here? And this is the greater than test. Can you tell me what that p-value is? What is the p-value for that test? Be very careful. What is the p-value for that test? Now, that's not what we're looking for, but let's just find the p-value for that test. The p-value for the greater than test, because remember, less than and then greater than, what will they do? So the less than, here's the less than, here's the greater than, and the greater than is this value right here. Here's where the greater than is at. So what value will that be? That p-value right there is going to be what? And how would we find it? Like the less than and the greater than always have this relationship. Correct, Layla, you got it. That's going to be 0.0066. But then remember, to get the two-tailed test, we go over here and double this. So that's also going to be another 0.0066. And this is going to be the two-tailed test when we double it and we add it up twice on this side so that we get kind of a doubling of it. CAD, you see it right here. You're right. So this is double the smallest, and we're just doubling these two together because this is the greater than the two-tailed. Does that make sense? You can see it here in other jump output. We had another jump output where you can see the relationship between the p-values. I guess it was this one right here. Oh, but the p-values are so tiny. We can't actually see them if they're... Oh, here we go. Here's one where you can actually see the p-values, and there's decimals you can't see in the background, but just think 21 times 2 is 42, and 21 plus 79 is the remainder. Yeah. So you can see the relationship where the greater than, the less than add up to 1, and then the does not equals test, which this is the does not equals alternative. The top one right here is double the smallest. Sometimes there's decimals you can't see. It'll show them to you right there. Yeah, and then this is rounding up right here. So if you hover over it, it'll eventually show you the p-value right there, and there's decimals you can't see in the background. Don't worry about those decimals. It's always double the smallest, and this one's so small they all just look very tiny. So that's got it. That's the test right there. I think you were saying Layla and Simran have the same question. Let's hop over to Canvas content. Okay, let's do some Canvas, not Canvas content. Let's do My Pearson. Did they make my DataCamp course? DataCamp, what are you doing? DataCamp, why? DataCamp, no. Let's see. Matt Pearson. The question is... Had Haley's first. Okay, thank you so much, Layla. Haley's question was age of football. Yes, we totally forgot about that one. Okay, let's do that. Haley, Layla, that's so awesome. Thank you so much. Let's throw, yep, you are totally correct. Let's throw some 50 points. Vols help Vols. We're so positive here. People aren't like, oh, Brian just doing my question first. I've got the recency effect. Whenever something's like, it's like, oh, we just talked about it. Let's do it. I think everyone does that. And let's do the... Here we go. We got this. Let's do it. Would DF greater than 10 not be a way to check for nearly normal? Nope. Does it say that as one of the options? No, the degrees of freedom would just tell us the shape of the t-distribution. If that question is talking about DF greater than 10, just by itself is not going to... there's other ways with the degrees of freedom I could maybe tell you if it's nearly normal, but DF greater than 10 alone is not going to tell me nearly normal, especially if it's a very skewed distribution. The DF of 10, degrees of freedom of 10 is not going to tell me it's nearly normal. I wonder if you're on the Discord, send me that question on the Discord. I for some reason, maybe I'm not aware of how that question asks. I thought I was going to talk about like a bar chart or something like that, or a bar chart we can use to check it. That's what I had in my head when I was thinking about what the question was asking. I was like, what kind of graphics? But maybe it's asking about DF. That sounds to me like DF, we don't... The more degrees of freedom, the more normal it's going to be. But let's check this out right here. Here we go. So this is a two-sample t-test, as in we have a categorical variable right here, baseball versus football players. We have two sample sizes, 28 baseball players to talk to, 29 football players to talk to. And we ask them the age of a player. We're just asking the age of a player. Baseball players were on average 26.66 years old, and football players were on average 25.77 years old. Standard deviation tells us the variation within each group, and baseball players had a variation of 3.84 from the mean, and football players had a variation of 2.64 distance from the mean on average, kind of a typical distance that they are away from the mean. So let's go ahead and take this data. I guess we can write the null hypothesis. Now, there's only one I can eliminate with our classic trick. Our classic trick is the null has the equal sign. So about which is not a way to check. Yeah. So I'm thinking it maybe has a bar chart on there, CAD. So yeah, good question right there. Does it have bar chart? Because bar chart, what kind of data is a bar chart for? Because that answers why a bar chart is not used. Just to flash this on the screen real quick so everyone can see. Oh, I've got it as a thing now. I can go right here. So if you look right here, bar charts are not used for quantitative data. Bar charts are used for categorical data, so we can't use the bar chart for that. We can't use it to check the nearly normal condition. So bar charts, no. Let mu1 be the age of baseball players, okay, and let mu2 be the age of football players. So the null has the equal sign, and we want to see, what are they trying to test? Okay, that suggests that baseball players must be on average older than football players. Okay, so which answer is it? A, B, C, or D? They're trying to show evidence that baseball players, which is the first mean, is greater than the second mean. That's what they want to show evidence of. So A, B, C, or D. They're trying to show evidence of, on average, baseball players are older than football players, which it's the first mean. So they're trying to show on average baseball players are older than football players. So if we were to take the first mean minus the second mean, we'd expect the difference to be positive. So that kind of gives away the answer. Is it A, B, C, or D? Which one? Which one do you think it is, Haley? Or I might have missed. It might have blocked the chat or something. Maybe did Mubot see that? Yeah, you got it. Yep, that's totally it. It's B. We're doing a greater than test right here, so that's going to help out. Now it wants the test statistic. So let's go over to a word sheet. Great job right there, Haley. Excellent work. Let's throw some more 50 points. Everyone's just getting ridiculous points these days, but we love it. And we'll go back to here. And thank you, puppy. Thank you, puppy. One of the things I want to do is I want to like film Morty on our portable green screen. I've got like a portable green screen, and I want to make a button where I can make Morty run across the screen. Like the video right here, like Morty just scurries across the bottom of the screen. I'm like, hey Morty, where you going, man? And like, I don't know, but I don't want to make him scurry. Like, I don't know. He'd probably just be laying there. I could just have him laying there, or like him like stand up. But we'd have to put the green screen around and like film him. And I don't know. Maybe I'll talk to Chelsea and like over the weekend, I'll be like, let's film Morty on the green screen. And I'll edit him out. We can make some green screen Morty graphics for the stream. So we need to know, well, it's got all the notation marked for us, so makes our life easier. The first mean is going to be y bar 1 and y bar 2 is the second mean. They noted that the baseball player was the first mean. I've got tons of ideas, and then some of them just like I had a big idea for the haircut thing, and then it just took way too much time. I think I've got one more thing I can do with it, but gotta cut the videos, gotta do a bunch of stuff, and between grading and stuff, sometimes there's just not enough time. It's like there's got to be more time. Not enough time to do everything. So sometimes you just go for priority, like have to grade papers, have to fix tests, have to do this or that. So you get the priorities done, and then you go towards what you want to do for fun. And luckily I have a lot of fun like making videos, and so I hopefully always have time for the fun stuff, but sometimes you got to do the things that you have to do. I have to be grading papers later today. I got a lot of papers to grade today. Oh no, a lot of papers to grade. And so let's go ahead and start multiplying. Multiply this right here. This is the way I do it. I solve the bottom of it first. 3.84 squared divided by 28. I copy that, and then I do 2.64, square that, divide by 29. I add together those, and then I square root, and we're good to go on the bottom. So the bottom has now been solved. The t statistic is looking pretty small right here. So let's go ahead and do 26.66 minus 25.77. And wow. Oh, I love it. I can tell you the p-value maybe. The p-value is going to be about 16%. Yeah, it's going to be very, very close to 16%. You're wondering, how do I know what it is? Well, degrees of freedom for this is a guesstimate. We'll find the degrees of freedom in a moment. I would say the degrees of freedom are probably about 54 or so. So a t with 54 degrees of freedom is going to look pretty normal. we found a t-statistic of 1 with a t-statistics of about 1 and it looking pretty normal. We can use the empirical rule. If I were to solve this on my own, I definitely know that the p-value is going to be very close to about 16%, and that means I do not reject the null. Now, we're going to solve this out more exactly, but at this point, if I'm doing this problem, I can basically give the answer that I am not going to reject the null because we definitely do not have a large enough t-statistic to obtain a small enough p-value. So here's the t-statistic round to 2 decimals. We need to go and actually find the degrees of freedom, which tell us the shape of the t. So let's show our numbers again. Here we go, 28 and 29. I said it'd be in the mid 50s. I said like 55, maybe it's 54. It's in the mid-low 50s. 3.8, it's gonna be like 52 now. 3.84, just make sure you put them in, like 28 goes with that, 28, 3.4, 3.84. I say 52 now. I say 52 degrees of freedom. 47. Not horrible, not a horrible guess, but a little bit less degrees of freedom than I thought. And what do we do with these degrees of freedom? This tells us the shape of the t distribution. So we're going to take the degrees of freedom right here and go to a t-applet and put this in to show the shape of the t, because the degrees of freedom control the shape of the t. Here comes the t-applet. Mubot, where you at? Do I need to drink some coffee? Yes, I do. Here's the shape of the t. We put in the degrees of freedom, and we put in our t-score. It's very important that we know we're doing a greater than test. And remember my guess of 16%? We were off by 3 thousandths. 3 1,000ths we were off. There's the tenths, hundredths, thousandths. So a guess of about 16% was very close because the t-statistic, and I guess probably if we round this the way they want it, it's still, it's a little smaller because it's further over. So yeah, 0.156 is the p-value. So we are definitely not rejecting the null at any reasonable alpha level. And there's the p-value right there, 0.156. So we definitely failed to reject the null. There is not evidence for the alternative. Good to go. Does that make more sense, Haley? I think we've got Layla's question next. But did solving through this right here, seeing the steps, finding the t-statistic, finding the p-value, did it make more sense? And I really liked how our t-statistic turned out to be 1. And using our knowledge of the empirical rule, we're like, well, we've got a lot of degrees of freedom probably because larger sample sizes. Yeah. So the big thing is, which I hope people can get to in this class, which I love that you can kind of do some of these things in your head, is when you see this t-statistic of 1, you go 68, 32, 16. And the empirical rule is so powerful because whenever you're using the t-distribution, if you have enough degrees of freedom, well, then your answer is going to be basically like the normal curve because this is basically 16%. Because going back to our knowledge of the normal curve from earlier on, whenever you're doing a right tail on the normal curve above 1 is basically 16% because within positive or negative 1 is 68. So then outside of that is going to be 32. And then one of those tails is worth 16. Now we do a rounded version with 68, 95, 99.7, but it still pretty much works. Like 68 is going to be here, and then 95, 95.449, and then 99.73 technically. But don't worry about those extra decimals. You got it right there. Let's go do, I think it was Layla's question next. Yeah, we'll go. Let's put on, what? I can't believe I messed up my green screens. Let's go here all to, let's do this one. Okay. Time for, the question was, Layla's question was, chapter 19. And the chapter 19 question was, well, we did that one. It was the political thing or something, right? Remind me of it while I'm loading this up right here. I think it was political or something. Chapter 19. Chapter 19. And let's see right here, Layla, if you can remind me. We've got the poll, respondents on a political party. Yep. I've got it right here. Let's go ahead and check it out. Let's do it. So what do you think? The chi-squared test of homogeneity or the chi-squared test of independence? A or B? Or independence or homogeneity? What do we have? A or B? What do we do this whole chapter? This whole entire chapter has been the chi-squared test of what? Have I been saying, let's do the chi-squared test of homogeneity? Or I've been saying, let's do the chi-squared test of independence? That also helps with the null hypothesis. The start right here, which is kind of a key to it, which will really help with the null and alternative, will be the what? Chi-squared test of independence, CAD knows it right there, and I'll even help out. CAD, thank you so much. Remember when we do the null hypothesis, we're going to look for independent. It doesn't always have to be there. Ooh, they're trying to trick us right here with this. No, 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 no. I'm not going to say that. They almost got me. Let's go to this other one. No, no, no. And here we go. I like this right here. We have independent, not independent. We're not going to say which way the association goes. We might look at it at the end and look to see what kind of way the association goes. But the null is that they're independent. The alternative is that they're not independent. Do remember that this could say something like they're associated, because that's what not independent means. It means they tell you something about each other. Doesn't mean they cause each other. It means they tell you something. Is this count data? Yes. Both variables are categorical. That's what count data means. Is it random? Sure. Do we meet the expected cell count? Let's go over here and start looking at this in jump for the expected cell count. Now I'm going to slow this down a little bit here. Slow it down. We're going to go to copy to clipboard. And when we copy to clipboard, make sure to hit Control-C or Command-C. When you hit Control-C or Command-C, it's going to copy it to your clipboard. And now that you have it copied, go to jump and go to a new data table. File, new data table. Under File, New Data Table, it's very important that when you go here, you make sure that you go to Edit, Paste with Column Names. That's key. So we're going to paste with the column names. When we paste with the column names, you'll see that you get a categorical column and three quantitative columns. With the three quantitative columns, we're going to go here to Tables and Stack. I think CAD knows. He's like, I got this. I got this. We're going to go to Tables and Stack. With tables and stack, we're going to stack the quantitative columns. Double click them. And I'm going to pause right here to make sure you went to tables, stack, and then you have your quantitative columns stacked right there on top of each other. So now let's go ahead and click OK with our quantitative columns stacked. So now we have our data sheet we can work with. It should look like this. Rewind, review if it didn't work, ask questions, let me know if it didn't work. But now we have the data inside of Jump in a way we can work with. So, Leanne, we got it. You bet. Let's do it next. Oh, which one do you think, Leanne? Which one do you think we've been using? Because here, I'll give a hint with this question. You ready? We're going to go to Analyze. You are correct, Leanne. Excellent work right there. We're going to go to Analyze Fit Y by X. And with the Analyze Fit Y by X, we're going to see if somebody's label, and this is actually gender right here, and we need to put the data. This is probably one of the key mistakes that happens, is that people don't put the... Really? People don't put the data right here, and then that causes an error. So make sure your data goes right here. Your Y variable of interest, we want to explain someone's label. This is gender. It has a blank there, but not the end of the world. So let's go ahead and click OK, and you can see down here we do have the chi-squared test of independence, where we are getting the Pearson chi-squared. Remember, the Pearson has your p-value. So the Pearson chi-squared test statistic is where the p-value is at. The Pearson has the p-value. 9.755. 9.755. And so we go ahead and enter in 9.755. And then there was a very small p-value if you didn't see in the output. And I'll bring the output back up here somewhere. 9.755 leads to a p-value. I'll stall off the screen. Leads to a p-value of 0.00676 right there, 0.0076. So what do we do right here? The p-value is well below alpha. Alpha is the point at which we reject the null. So I reject the null hypothesis. There is evidence for the alternatives to support the claim. Did I skip a question again? The expected cell frequency is met, and we can check that. We need to have at least 5 expected cell counts. The smallest expected cell is going to be this one right here. And we can show its expected cell count to show that it's greater than 5. I believe it will be. I've done this problem a few times. And here's the expecteds. I'll show how to find this mathematically too. There's the 18.766. I guess we need the counts also for it to show us. There we go. This is the smallest expected. It does have the smallest count. Ignore this count. That's just there to trick you. The smallest expected will be the smallest row total and the smallest column total where they meet. So the smallest expected amount is female independence. And let's go right here and go 92 times 41 times 201, or 92 times 41 divided by 201. And there's the number right there that you see, a little less rounded, but that is how that number is being obtained. Row total times column total over grand total. All this good stuff right here. You should also know how to get the chi-squared test, or the chi-squared cell chi-squared from this, which was, and I'll repeat the process, and we should see it right here. There's that number right there that I just calculated. It would be the observed, which is 13, the observed minus the expected, observed minus expected, quantity squared over the expected. And so I'm able to calculate these numbers in practice and know how these numbers are calculated. Now, we are letting JMP do a lot of the heavy lifting for us, but we should know how these are calculated. Like, I should be able to calculate the row totals, the column totals, the grand totals, the expecteds, the cell chi-squareds, and just know how this table works right here. We more focus on, at this point, the expecteds and the cell chi-squareds. Knowing that the counts would add up to the row totals is also good. Did you do the one where newspaper headlines, time, and I don't think we've done that one yet. It's a good one right there. I think so, right? We did Leanne's question right there. Let's do this. Let's take a look at that one. Music between. I'm trying to like play a new song. Let's play a new song. We don't play this song, so let's just go here. Let's play this song. It's like intense music right here. Newspaper headline. Let's find it. New music for today. Brian's clicking the buttons he never clicks. We did do this one, but let's do it again. We're just chilling out. We got 40 more minutes. We got so much time. Let's do it. Going back in time right here. Newspaper headline. Newspaper headline at the time, traditional wisdom in succeeding decades have held that women and children escape a sunken ship in greater proportion than men. Here's a table with the relevant data. Do you think that the survival was independent, which sounds like the null hypothesis to me, of whether the person was male or female? Just defend your conclusion. So we have right here the null hypothesis is that someone's gender and their survival is what? We're doing the chi-squared test of independence, and the null hypothesis is going to be that the two are independent of each other. The alternative would be that there is an association. I'm just making sure we don't have an error right here. Dependent, no. Is an association, no. This one, I'm trying to see why this one's wrong. You know, I'd almost say they should think over why they did this. I need to talk to my Pearson people and say, you know, theoretically, don't think that one has an error. Sometimes I wonder about the people writing the questions. I wouldn't phrase it this way. That would not be my favorite way to phrase it. There's no association. That's kind of what the null says. The null pretty much says there's no association. Yeah, no, but this is the one right here. Use the independent. That's the best way to doing it in my view. So I'd use independent. Are the conditions satisfied? We definitely have more than enough expected cell count. Expected cell count means we have at least 5 expected cell count. Let's take the smallest row total, the smallest column total. So smallest row total times smallest column total over grand total. And that's the expected cell count greater than 5, so we're good. This is count data, which means they're both categorical. Are they random? Are they less than 10%? Maybe. We don't want the groups to be dependent on each other. We want them to be random, so we'll assume. Now, this is where we need to go over to JMP to make our lives a lot easier. You know what? Let's not use JMP for this one and do it a different way right here. Let's do the whole thing by hand, which is going to take about the same amount of time to do it as JMP. So here is working the problem by hand, which takes a moment. Okay, so let's calculate our expecteds right here. Okay, so we need to get, these are all the counts. Not bad practice to do this by hand. Counts. Those are all the counts, which are the observed. So I'll call them the observes. It's called count data for a reason, because they're counts. But you can also call them the observed, which will help more with the next formula. Observed and counts are the same things. Like this is how many we count in each group. This is how many we observe in each group. Synonymous words right there. And we want to make the expecteds now. Can anyone in the chat calculate this expected value for me? What would be in that cell as I go through here and do this? I want you to calculate that expected value for me as I go through here and do this. So calculate that expected value for me as I go ahead and do this. So that's your goal, chat, right now, is to calculate the expected cell count right here. So go ahead and calculate that, because I might make an error. If you see me make an error in any one of these, tell me. Okay, 155. There's that one. We're 1/8 done with all the calculations. I'm taking all the row totals times column totals over grand totals. There's dividing by the grand total. I'm just finding the lower one right here. 34338. And then I'm going to do this one up here. So that's row total times column total over grand total. Just line them up. And 668 times 6. There we go. And let's see. Can we get the bottom one in chat? Let's find out. 51238. How about we do the bottom one? There's the answer to the bottom one. Did kind of a reverse solve, and actually you only need to solve one of these to get all the remainders. Interesting thing you can do right here. Something I haven't mentioned, but it's just more theory, is that all of the cell chi-squareds add up to the totals. So I was able to find this one in another way by saying, well, all the expecteds add up to the totals. So I just subtracted this from the total and got that answer. I just subtracted from 1643 the 512 because I know the expecteds have to add up to the totals. That's not a conventional way of solving it, but it's a theory way of solving it. I can solve it the conventional way with row total times column total over grand total, and we do confirm the same answer right here. So these are all the expecteds. Now that I have all the expecteds from the, and let's show the formula again, almost dropped the pen today, row total times column total over grand total right here. And that obtained this value right here by row total times column total over grand total. So that is the expected cell count right here. Now we have to find all the cell chi-squareds. So now we got to get all the cell chi-squareds. Great job, CAD. Excellent work. Cell chi-squareds. It's not chi-squareds, it's chi-squareds. So now we have to do the observed minus the expected squared. So here, let's put the formulas here. Formulas for this one is row total times column total over grand total. And the formula for this one is the observed minus the expected squared over expected. There we go. Observed minus expected squared over expected. And let's take a look. We're going to take the observed. We almost have this. 382 minus 155,617. And we square that, and we divide by 115,617. No way. Come on. That's not right. Let me double check. Really? I know some of these are big. And maybe that's where it's coming from. You get a big chi-squared at the end of this. You get a very big chi-squared, so I'm wondering if that's right. Let me double check the math. Observed minus expected squared divided by, yeah, there you go, 329.33. I haven't solved this one by hand in forever. And we take observed. We're doing the bottom one right here. Observed minus expected. And square that. Divide by expected. 149.25. And next we take the observed minus the expected. We square that and divide by the expected. 100.02. And then we take the observed of this minus the expected of this. So we're just doing the formula right here in red, taking each observed minus each expected, squaring it, and divided by the expected. I did my jump, and yep. No, that's very, it'll be big. This one is very, yeah, and it's great job, Layla, right there doing it in jump. It's not bad, especially since, you know, you'll do ways like this on the test to practice this, or just like to solve this one time by hand. It's just a lot of cumbersome work. I'll speed run this one in jump, and you'll see it'll take me seconds to do in jump. Now you need to sum up all of these. So the sum of all of these. So now we need to take them and sum them all up to get the Pearson chi-squared test statistic. So that's the last step right here, is to sum them all up. So good theoretical practice. So I'm just adding up that one. If you make one error typing these in, hopefully you have one of those calculators that shows everything. Yep, so I'm getting this right here. And if we go back and we'll double check the work. I'm gonna see if working it by hand. I clicked. There we go. Round to 2 decimals. I get this right here. Working it by hand. The p-value is going to be 0. Graphically, I'll show graphically what that looks like. Graphically speaking, I wish I'd just, oh, good. Graphically speaking, the distribution, it has 1 degree of freedom. So a chi-squared with 1 degree of freedom looks something like this. The tail goes to about 10 right here, and we're ridiculously overhead, 600 something. So the area under the curve is basically what, Layla? So you see this in jump also. We're so far off the curve right here. You have to do like a little, like, in the future, when the curve is way off here in space, we have 1 degree of freedom because it's a 2 by 2, 1 times 1 degree of freedom. We're completely out here in space. You can see the 1 degree of freedom one right here. Like I said, it goes to about 10, and we're over here at like 600 something, and the p-value is, you don't even see it. So with a chi-squared of about 600, it's not even saying 600. It won't even let you calculate that high, because it's like, nah, it doesn't even exist. We're way off the curve right here, and that's the chi-squared with 1 degree of freedom. Very, very skewed distribution. So we would definitely reject the null hypothesis, and there's strong evidence. Now, before I enter this in, because I'm not going to get any questions wrong today, let's speed run it right here. We're going to copy the clipboard. We're going to bring it over. We did this one earlier. If you're watching for a slower run of this, check out the videos from earlier today where we do a slower step-by-step of bringing these over right here. So we're just kind of speed running this right here, because we're just going to check that chi-squared test statistic. And there we go. And the chi-squared is 623.93. Did I get exactly that? 623.93 on the dot. Wow. Whew. All that work right over here. All that work worked out for us. All of that worked out for us. We took our observes. We found all our expecteds from row total times column total over grand total. Remember right here that these are the row totals. These are, well, that's not a row total. These are the row totals. And these are the column totals. And this right here is the grand total right here. So you do each one of those and find for each cell the row total times the column total over the grand total. And then you have to take your observed minus expected squared over expected, find all of your cell chi-squareds, then the sum of all your cell chi-squareds is the Pearson chi-squared test statistic. We then plot the Pearson chi-squared test statistic on the appropriate chi-squared with the appropriate degrees of freedom. Really good practice right here on this one. It's a chi-squared with 1 degree of freedom, and it was 629 point like 623 point 93. That's got it right there. Excellent work, Layla. So does this problem make a lot more sense now? Does it, like, we did all the steps here by hand, so this was a really good review of today's lecture. Like, if you watch this and you're following the steps, you're like, okay, he's finding the expecteds, he's finding the cell chi-squareds, he did his null hypothesis. This whole question teaches today's whole lecture. If you understand like why we get the degrees of freedom, it tells us the shape of the chi-squared distribution. And there's the shape of the chi-squared with 1 degree of freedom. Remember, we did 1 degree of freedom because this right here is a 2 by 2. The degrees of freedom are rows minus 1 times columns minus 1. So we do rows minus 1 times columns minus 1. So awesome, Layla, amazing work. This is one of my favorite chapters. So yeah, it's 2 minus 1 times 2 minus 1. And that is equal to 1 times 1, which is 1 degree of freedom, which is, so then we get df equals to 1 right here. That's why we're getting this right here. So the df, the chi-squared with 1 degree of freedom, it's a very, very right skew distribution at that point. But yeah, that's a good problem right here to solve and just practice understanding what the observed are, the expecteds are. These are by random chance given the null is true. Here's the standardized difference are the cell chi-squareds. Sum them up, get your Pearson chi-squared test statistic. Plot the Pearson chi-squared test statistic on the chi-squared curve with the appropriate degrees of freedom. And here's your p-value. So let's mark that. P-value equals 0. For all intents and purposes, it's 0. I don't even think I can get R to tell me a p-value on this. So this would be p chi? Oh, it is there. It is there. P chi-squared? Okay. I haven't used this one before. So with the distribution of the chi-squared, we want to go to, and it should have, let me look at the format of it. No. So we put in the value we're testing, and then we put in the degrees of freedom, and it's going to tell us the area to the left of the curve, I think. That's what I thought. It's saying 1. It's ridiculous. Yeah, it can go pretty far out on decimals. Oh my gosh, I thought it would at least start showing decimals now. No. There we go. Is my Saipan? Really? If you have, is the, so here, chapter 17. 2 seconds, I want to see something real quick on this. I shouldn't do all these things. Oh. I shouldn't make changes to my R. There we go, that's what I want to see. I want to see where it would calculate this out to. Yeah, you see after a certain point, yeah, it's after the p-value is getting so small, it's not even letting us calculate it any further out, and it won't let me show the digits past this. It's saying, nope, you can't even do that. And I'm like, come on, calculate it further out. Why not? You're a computer. Do what I ask for. This is chapter 17, but can you read the one that says the study examines the fact content in, yeah, let's do it right here. Let's hop to space. Man, I want it to calculate. So if you look, I can't calculate past 70. So for all intents and purposes, the area to the left of it, which would be 1 minus this, at 70, it's whoa! Oh my gosh, that's like Christmas right there. Well, now we're stuck. It's not giving us any answers. Yeah, after about 70, it's estimating it to be 0. It's like, nope. It shouldn't have shown me that. That got me all excited to be like, oh my gosh, we can. I swear it showed it, didn't it? Yeah. Very soon after that, the program says, nope. Yeah. I don't know why it didn't change there. Okay, I'm done. I don't know why it's not changing. It should change. Let's head back to space. I start to see things and I ask, I have a lot of questions in my head. I'm always like wondering things like, how does this work? What's going on with this? Why is it calculating it this way? And I'm wondering why the numbers, I wonder why it's not changing it. Now that makes me want to question R for a little bit here. Here we go with the fat content in hot dogs. We got a different version today, so let's take a look at this. So here we are with the fat content in hot dogs. A study examined the fat content in grams for beef and meat hot dogs. The resulting 91% confidence interval of meat minus beef. Now, since this interval is negative, which of these had more fat in it? So imagine we think that the true difference between the meat and beef hot dogs is contained in the interval negative 6.4 to negative 3.5. So since this is what we think the true difference is, which of these had more fat in it? Like, which had a higher fat content on average? Not saying every one of these will have more fat, but on average, was it the meat or the beef, since the entire interval is negative? Since the entire interval is negative, one of these, on average, we expect to have more fat. And so I think the entire interval is negative right here. So since the entire interval, because we're trying to estimate the difference between these, and we're like, I think the difference is negative. Like if I take the average meat hot dog and the average beef hot dog and I subtract their difference, we'll probably see a negative difference. And look at the way you're subtracting them. Right, Layla. Yep. Since it's negative, it goes with the second number. Just look at where the negative is at. It's with the second number. And since the interval is all negative, we think there's a true difference where beef hot dogs have more fat content in them on average. The endpoints in the confidence interval are negative numbers. This indicates to us that the beef hot dogs, the mean fat content is probably higher for the beef hot dogs. What does the fact that the confidence interval does not contain zero mean? This means that the difference is statistically significant. So there is a significant difference between the two. And then if we were to do a test on this, so think of the way confidence intervals in test works. If we did a confidence interval, what kind of test would we be doing here? 91% confidence interval is the same as using a what percent alpha on this. 91% confidence is the same as a what alpha level. So just think of complements. Because when you do a test and when you do a confidence interval, so we're doing a 91% confidence interval, this would be the same as doing a two-tailed test with this alpha level. So when you do a 91% confidence interval, 91%, that would be the same thing as doing a two-tailed test with an alpha of what percent? So if there's 91% shaded on the inside there, then what would be on the outside, like the two-tailed test? We call it like the complementary, or it would come to the same conclusion. And this is why values we would look at, like we would reject 0 as a value using this alpha level. Using a blank or blank percent alpha or 0.0 this alpha, I can reject 0 as a value. And because I know it's not in my confidence interval, I'd also reject it on my test as a value. So how can we go from the confidence interval to the test? Remember, they're just complements. So the alpha in a percent would be what percent? So if it's 91% confidence interval, the resulting two-tailed test that does the same sort of mechanics, like they would just come to the same conclusion. And the truth is, you can just make confidence intervals. They'll do tests for you. Because any value inside a confidence interval is a value we would theoretically believe. So we can always just look at a confidence interval and be like, oh, those are possible values. So the resulting confidence or two-tailed test would be 9%. Because we got 91% inside, 9% outside on the two-tailed test. And yeah, that should do it right there. Awesome. What other questions are there? If you got questions, let me know. Let's take a look. We already played that one, right? Great job, Layla. Yep, 9%. What questions are there? What questions are there? Let me know if you have a question right here. No worries, no worries. Yeah, don't worry. Sometimes I realize people are working along. Oh, I need all the coffee. I'm gonna be so. It's like the weekend comes, I'm like sleeping in. I'm like, oh, I love teaching, but the only thing I don't like is waking up in the hour of 7. It's the only thing I don't like. Like other than that, I love teaching. I love doing stats 1, but waking up early is just not so fun. When you get to like. Those mornings you wake up where you don't set an alarm are the best mornings. Like when we don't have like a. Can you go over one do you think would be good for the exam? I finished my work, so yeah, let me do this. Let me go look at some exam questions and talk about what might be good on the exam. Those mornings when you don't have an alarm going off and you wake up and you wake up and you're totally awake and you're like, I'm gonna get out of bed. And you think, no, I should lay over. And you're like, nah, I'm good. I feel totally awake. I am not tired. I'm going to get up. I'm going to make some breakfast. And then you think about coffee. You're like, I don't need coffee. Or you forget your coffee. You're like, wait a minute. I didn't drink coffee this morning. And then you're like, oh, because I'm wide awake. Okay, let's see right here. Yeah, let's start with this. Oh, I love this. You guys got this. Okay, here we go. Let's talk about the central limit theorem, which is something we haven't talked about. I'm in national. Yeah, I know, right? That's what gets me too, Layla. I'm in the other time zone too. Some people are in like California, and they'd be waking up at like the hour of 5 a.m. to take class at 7 a.m. Would that be right? No, 6 a.m. Oh gosh, 6 a.m. class. Woof. Just gotta make sure you go to bed like 9. According to central limit theorem. Yeah. Okay. Wait, is this a repeat question? Why is this question on here twice? Really? I'm going to make some changes here real quick, Layla. I'm going to go look at this. Why does that question appear twice? I was like, I like that question. And I saw it twice. What have they done to this? 2 seconds right here, and then I'm looking at some stuff. Is it seriously the same? There says there's 2 questions. That is an identical question. And I literally got both of those. And it was only supposed to... Okay, let's go ahead and click OK. And that should remove it. And now I shouldn't see that. Okay, good. And let's go back. And it should... There we go. Okay. That's a tough one. Okay. Let's take a look at this right here. Put a little music. Okay. So let's talk about the central limit theorem just briefly here. And let's take a look. Okay. So the central limit theorem. The central limit theorem says 2 things. What 2 things does the central limit theorem say? The central limit theorem says 1. The distribution will become more normal as the sample size increases. So we can see this. Let's go take a view of this. What are we talking about? The distribution will become more normal. So let's go here to central limit theorem applet. With the central limit theorem applet, really easy to see this. We can see here a skewed distribution. And if we increase the sample size right here from something like 2, let's start with 2, it looks a little bit more normal. But if you increase it to something like 25, and we're taking the average of 25 observations, so you have to take 25 observations, take the average, the distribution of the mean will become more normal. There it is. You can have things that are even really skewed. Like you go here to something like this right here. And if you increase... Ooh, this is going to be a crazy one. We might not have a large enough n right here. So if you only take 2 observations and average them, you see the following. There you go. We're just going to keep doing this. And all we're doing by clicking here is speeding up the process. And you see, that doesn't look normal. It's more normal. You might say, is that really more normal? Yes, it is. It's more normal. That's what the central limit theorem says. Now, if we were to increase to a higher end where we take 16 observations and average it together, we take the mean of all 16 observations and we start building a new distribution. And take a look, as you do this process repeatedly of taking 16 observations and take the mean of those, you start to get something that also starts to look more normal. And at that point, you might say that's starting to look normal. Now, what a large enough n means is that if we do a large enough sample size and take the distribution of the mean of that sample size, we should see something that's approximately normal. And at this point, we might have a large enough n. Maybe we need something closer to 100 because that's heavily skewed. This is where if something is normal, it only requires a sample size of 1. If something is skewed, it requires a sample size of 25, and heavily skewed 100. We kind of say that on the test. We say like it's heavily skewed, and so sample size 100. But another important thing to see is the second characteristic, which I'll write down here in a moment, is that the distribution, let's say it's normal to begin with, well, it's going to be more normal, but it'll also be tighter. So the distribution right here is tighter, and the standard deviation is the original standard deviation over the square root of n. That's 5 right there up top, and that's 5 divided by the square root of 25, which is 1. So as n increases, like here's a small n, as n starts to increase, the distribution gets tighter and tighter and tighter. So we see right there, theoretically speaking, the 2 things that the central limit theorem states, that the distribution of will become more normal as the sample size increases, the distribution will get tighter as the sample size increases. By tighter, we mean smaller standard deviation. Kind of 2 very important facts right there. Go ahead and look over here. Yeah. That's tricky stuff right there. Trying to see if I see anything else really great. There's a lot of good questions on this. There's a lot of good questions. So many good things. A lot of these are Canvas content questions. Let me talk about this right here real briefly. How can we, I'm trying to like not directly do a question, but I'm literally looking at test questions and talking about stuff. How can we change the margin of error Sorry, everyone right there. Trying to find, like, not sneeze on the computer and everything. I was like, what do I do? Sorry. I was like, I don't want to sneeze in the microphone. Ah! Anyways. So, how can we change the margin of error for this confidence interval? So, what two ways... I mean, I guess there's a third way, but we don't really have control over that. There would be three things in here, two of which I would say we really can control. What two ways can we change the margin of error for a confidence interval? What two ways could we change the margin of error for a confidence interval? So there's two ways to change the margin of error for a confidence interval that we really control. The two ways to change the margin of error is going to be right here with that star specifically, and right here with the sample size. Now, technically, the standard deviation does, change sample size and change the confidence level. Great job, Layla, right there. Excellent. So those are the ways to change the margin of error for a confidence interval. Like if you're talking about the margin of error, and so any confidence interval, like if we do a different one right here, we'll do it in orange. P hat plus or minus Z. Z does not have degrees of freedom, but we do get to pick this. And we don't really control P hat, Q hat. You could say, well, those do control the margin of error to a certain degree, but we don't really control them. We don't pick our sample proportion. So we can't control the sample proportion, but it does come into play somewhat in the margin of error because it helps create the standard error. But the real elements of control we have would be this. And we could draw the last one on here. Why not put all of our confidence intervals all together in one spot? Y bar 1 minus Y bar 2. Let's draw this a little bit better. Y bar 1 minus Y bar 2 plus or minus T degrees of freedom via the complicated calculator, square root S sub 1 squared over N sub 1 plus S sub 2 squared over N sub 2. So once again, this really boils down to, and I didn't put the star, very important, meaning we get to pick it. And once again, it boils down to this right here, that you can control the percent confidence or you can control your sample sizes. Does that make sense right there, Layla? Really good questions right there to kind of review and go over. I'm trying to see what else I can allude to. Do you remember about the T distribution? The guy who made the T distribution and where he worked at? Kind of crazy story right there with William Gossett. We talk about Mr. T and the T distribution. So you've got here the normal, and you've got here the T. Horrible drawing. There we go. The T is going to have thicker tails than the normal. It's going to be more stretched down. And technically, it's a little more like this. I can never draw it. I can never do it justice. You know what we could do? We could look at it. Oh, it's so hard to draw it. I just always draw it with the fatter tails. So the T is more smashed down. The T has fatter tails. It's technically tighter towards the middle of it. To see it more specifically, let's go look at it. And this was from William Gossett. So we want to go to our T applet. William Gossett at Guinness Brewery even, made the T distribution. And that's not a T distribution right there. That's the sampling distribution of the sample mean, which is actually the normal curve. That's actually the normal curve. It comes from a normal and then is used by the normal because we know population mean and population standard deviation. But the T distribution is right here. And you'd say, well, Brian, basically that's the normal, right? It's the normal when we have enough degrees of freedom that it looks basically normal. But when we have very little degrees of freedom, it's all smashed down. It's a little more bendy here in the middle. You'll see it starts to get that more kind of pushed out shape when it's more normal. But the T is a little more tighter with the fatter tails. The fatter tails are way easier to see now because usually by 3 on the normal, we're basically at the edge of the curve. So you can see 3 is right here. And if you go to the normal, 3 is over here where there's like no area under the curve. So the T distribution, I wish they didn't change the axis on theirs. Or maybe they always show T to 4. They do because of the tighter tail, because of the tails going out further. They show the T to 4. I don't know. I wish I could talk to this person and say, hey, maybe you could show the normal to 4 also. Everyone does the normal to 3 because the normal doesn't have as much area under the tails, but their T distribution always has the axis going out to 4 standard deviations. So you can definitely see there is no area under the tail here. It looks pretty much just like the normal with that tiny bit of area after 3. Just like on the normal right here, which is a little more zoomed in on the graphic, you can see very little area. That's because when you have a lot of degrees of freedom on the T, it approximates the normal. But when you don't have a lot of degrees of freedom, the T looks more flattened out. And it's technically tighter there in the center, which is hard to see. So my drawings never truly do it justice, but the T is basically a flattened down normal. It has more variation in it. William Gossett from Guinness Brewery made the T distribution to more exactly calculate these intervals because there was errors in the calculations. He's like, hey, we're doing this wrong. And it was Ronald Fisher was like, whatever, brewery dude, I'm not listening to you. And so he published it under the name Student T. And he was like, well, how about Student T? Does he know what he's talking about? Everyone's like, whoa, that Student T guy knows what he's talking about. He's like, yeah, I'm the brewery dude. Now I'm going to be known in statistics for calculating some stuff. Oh, if anyone misses that, I'd be so sad. Oh, cool. Let's talk about this real quick. This is good stuff. Oh, we got this. We got this. Okay. I want you to tell me which of these statements are true or false. You ready, Layla? We'll do this to end here. Let's write a few statements. When the p-value is low, okay. What do we got here that's true and what do we got here that's false? This might answer about 6 points to 8 points on the test. This, I just literally saw like 2 questions that kind of cover this. And what do we mean by low? If anyone's wondering, what do we mean by low? Low means below alpha. So low equals below alpha. Alpha is usually assumed to be 0.05, and that's your rejection criteria. So when we say the p-value is low, we're just saying we have a p-value that is lower than the value of alpha, which is usually assumed to be 0.05. So which of these statements are true? Which of these statements are true right here? Ah, very close, Layla, very close. Oh, wait, so, yeah. So which ones do you want to go with? Which ones are true? Which one of these are true? Which ones of these are true? Ah, you're seeing it. You're seeing it. So which of these statements are true? So which ones do you want to go with? Like, which statements do you want to say? Good practice, right? Good practice. I'm glad we put this up here for good practice. So which of these statements are you going to go with are the true statements? Put a lot of different things on here. This would be a decent test question if it just said, like, check all the ones that are true. It's pretty tricky. I feel like a lot of people would 1 and 2. That's it. The rest of these are false statements. We never say this except word. That is just, that alone is like a no-no. We don't accept the null. We don't accept the alternative. We either reject or fail to reject the null. We don't say anything is true. We're just saying we either stay with the null or we reject it. And that's what not rejecting means. So you could say, like, additional true statements. I'll write a few more additional true statements on here. When the p-value is low, we have evidence for the alternative. So when the p-value is low, we have evidence for the alternative. That's a very true statement right there. When the p-value is high, we fail to have evidence. The alternative. You could say we didn't find enough evidence. We fail to have evidence. So when the p-value is high, these are both true statements right here. Just means we didn't find enough evidence. So be very careful. I can see how mistakes can happen right here, but both of these are true statements. When the p-value is low, we have evidence for the alternative because we reject the null. So we reject the null and we have evidence for the alternative. Let's highlight this one right here in yellow because it goes with this one. This is just complementary. Like both these statements would be said together. Stop highlighting all that. Just want to highlight this. Okay, we're not going to get that one because it won't do that for us. And then this one right here would go with this statement right here. Or not. So I think that's a good spot right there. Those are true statements down there at the bottom. Everything else is just false, trying to mislead you. So these are true statements. When the p-value is low, we reject the null. When the p-value is low, we have evidence for the alternative. You could say we don't have evidence. Like, there's just a lot of ways to say it. We fail to find evidence. We don't have evidence. But we either have evidence or we don't have evidence. If the p-value is low, we have evidence for the alternative. If the p-value is high, we don't have evidence for the alternative. If the p-value is high, we fail to reject the null because we don't have evidence for the alternative. All of these right here are bad. We're never saying the null is true or false. If we're talking about type 1, type 2 error, we can talk about what would happen if the null was true and we rejected it, or the alternative is true, theoretically speaking. And that's when we talk about making a type 1 error. But we don't base type 1 error, type 2 error off of talking about our test results. We're not going to say our null was true because our p-value is this. We're not going to make that statement. We don't try to make statements about truth about the world, but we do talk about the errors we can make by rejecting the true null. So you will hear things like talking about the null being true, especially with a type 1 error. Because in a type 1 error, the null is true. In a type 2 error, the null is false. So good stuff right there. Any last questions, Layla? I hope this last part helped right here. We definitely did some test relevant questions. It was kind of a speed run. So I'll make sure to mark this in the video that, I was looking at the test right there and just straight talking off test questions. So some really good help here at the end. 100% test relevant because I'm down here looking at the test right there. Someone's going to try to like zoom in on that. But I was down there looking at the test and being like, oh, it's kind of a theoretical. Good job. Awesome. Glad to hear that. I'll hop back here to space. Well, great work. We are doing Kahoot tomorrow during class. Oh, you should watch. I know. Don't worry. It's all right that, like, I saw the Kahoot. I saw your message. So if you didn't see it, check it out. Oh man, someone's gonna be like super happy. Check that out. That's insane. And that's because everyone's been donating their prizes. We had 2 people donate their prizes, and I think second prize last time didn't collect their prize. So I just kind of said, okay, well, I'm gonna put it into that. The person who won the first Kahoot donated their prize to the final. The person who won the second Kahoot said, I'll donate too. And I was like, you can take it. And they're like, I kind of like send the email. I was like, yeah, take it if you want it. Like, it's just, they're like, no, I'll donate it. And I was like, okay. So pretty crazy right there. First prize, second prize, third prize. Pretty cool. It's the biggest we've done. And also do the what's it called? TN voice review right here. Do the TN voice review. And this was the advice from Zach right here on how to ace the test. Zach was saying, watch the speed runs, watch the Canvas content, watch the practice exam. I panicked during Kahoots because of the timer. No, don't worry. It's for fun. It's for good practice. And, we'll be doing a lot of review. And I need to make adjustments to the exam tonight. So that way the Kahoot questions are on there. So expect the Kahoot questions again. Just remember during the exam, you get to take all the time you want. So the Kahoot's almost like a practice exam then. Like the Kahoot has exam questions and you get to practice the exam and you get to be a little more intense setting to get to the exam and then just calm down. Just went back to throw up. Oh, you too, Sam. Thank you so much, Sam. We're going to play an ending song right here. Let's go to motivation. Oh. It's inspired. I hear all the songs and it reminds me of moments in class. Let's throw out 100 points. Why not? Sam, so good to see you. Layla, good to see you too. We'll be back here tomorrow. So stay tuned. We'll hop to space. We'll be back tomorrow. We'll be playing some Kahoot. You're welcome. I'll see everyone tomorrow morning. Bye for now, everyone. Bye. Bye, Puppet Shark.